Hi everybody, welcome to my YouTube channel, Lead Art Sci. Lead is for literature, art is for art, and sci is for science. My name is Zainab Kordi. I have PhD in quantum optics, light matter interaction, and nonlinear optics. In today's video, I'm going to talk about one of the optical property in the nature, so Talbot effect. So let's move on. So I did this project as a seminar for the course Advanced Optics. Um, the teacher of this course was Dr. Muradi, and I did this project when I was PhD student at University of Zanjan. So at the beginning, I will tell you a little bit the history of Talbot effect, how this phenomena was discovered by physicists and scientists, and then I will talk about Talbot effect. What is Talbot effect? What is the application of this effect? The real example of Talbot array illumination and Talbot actually pattern through the nature. For example, a honeycomb actually is a real pattern for actually describing how we can have symmetry through the nature and how we can have pattern through the nature and so on. So yeah, let's move on. So two questions that I'm going to answer. The first question, what is Talbot effect? And why we want to know about this natural and optical phenomena in the nature. So what does Talbot effect mean? So the self-imaging of a grating when it is illuminated by a monochromatic plane wave. But you might ask these questions. What is self-imaging? What is grating? And what is monochromatic plane wave? So actually this is completely right questions because for many years physicists and scientists had this challenge that what is light? Is it a particle or is it a wave? And actually light sometimes behaves like a particle, sometimes behaves like a wave. So Newton actually was treating light like other particles. And he considered also light as a particle element in the nature, which was not wrong, it was true, but it was not enough. And then Huygens actually discovered the wave behavior of the light. So one of the most famous experiment that I can refer to it is this double slit experiment, that if you actually illuminate some light to this double slit experiment, and then you put also special screen to detect what will be happen after light passing through this double slit. So in this regard, it completely depends how you measure actually and how you can see the light to see different effect and different detection on the screen. So if you just actually close one of the slit, so light just, so I mean the light, the beam from your laser beam, from your laser source, light source, has just one possibility, one slit. And on the screen, you just can see some dots. It means that the light actually is behaving like a particle, which is true. But now, if you just consider the two slits are open, and so actually this light beam, electron beam, so simultaneously has two possibilities. So first slit and second slit. And then you can see different effect on the screen. You can see patterns. You can see interference. It means that light actually behaves like a like wave. And Huygens actually for the first time discovered this, and he said actually this light actually contains some small little field with a wave packet, and this superposition and summation of this little wave packet actually can create a bigger wave packet. And so yeah, because of the definition of the wave for the light, for the first time actually was discovered by Huygens, we can see the pattern, we can see interference. But this interference actually can be destructive, and then so they can actually delete each other. The amplitude will be zero, or it can be constructive. And the amplitude actually is not just zero. So the amplitude of this wave packet can be summed up, and you can see actually the intensity. The intensity increases, and you can see actually the amplitude. You can see more light, so it's bright, and this combination of bright and dark, so this interference, so you can say that this interference pattern, so based on this concept in optics, actually they made grating. So grating, it's a small optical device that actually you can create diffraction for your light. And in Talbot effect, this diffraction actually happens in near field. It means in close distances from the source, light actually interact with itself, and then you can see self-image. And this self-image actually create a pattern. And this pattern actually, for the first time, I will tell you in the next slide, that this pattern actually, for the first time, was discovered by Henry Fox Talbot, a British physicist. Okay, and about monochromatic plane wave, I have to tell you that when I was bachelor student, my teacher told me that we never could have the monochromatic plane wave in laboratory, which was not actually wrong. He was right, because if you want to actually create a monochromatic plane wave, you have to choose just one frequency, and the white light actually is the spectrum of different frequencies, and it's very, very hard to actually to choose one exact frequency of this spectrum. But nowadays, so many physicists, experimentalists, especially in the laboratory, if you talk with them, yeah, they are with a very, very good approximation, or maybe very exact, they can create a monochromatic light. Okay, so now I was explaining little by little everything about Talbot effect. So let's move on a little bit more history that I mentioned, and also the second question that I asked was why we want to know about the Talbot effect. Is it important to know? We can say, yeah, it's important, because in optics you can do a lot of precise measurement, because you are dealing with light, and light is about photon and electron and the atom, which is a very, very fine structure. It's very, very small. And if you want to actually do a very, very small measurement, so in optics, in metrology, you can use the optical devices. And it is important to so Talbot effect was a good discovery, actually, that they can use it in optical array illumination, optical measurement, and especially, for example, optical interconnection, because optical network, optical lattices is something that physicists are working with it. And so it's about interdisciplinary between, for example, complex physics, optics, and in optical interconnection. So you are actually dealing with a complex network, but optical complex network. And also it's about another application, matter wave self imaging. Okay, let's move on. So a little bit history. History is always important. So Talbot effect is a near field diffraction effect that had been observed in 1836 by the English scientist Henry Fox Talbot. So you can find this in this paper that I actually referred to it, and also you can even search about Henry Fox Talbot in Wikipedia, and see the history of this phenomenon. And this phenomena actually was theoretically interpreted for the first time by Rayleigh. So if you are interested in, you can actually check the Wikipedia page for Rayleigh radiation, Rayleigh scattering. So he did a lot of good measurement in optics. Okay, in 1988, scientist Adolf Lochmann illustrated Talbot array illumination, so a little bit further. So now we are dealing with arrays, and in these arrays, actually, you can search for symmetry, so and parity. So and so in 1988. So I was talking about this, yeah. So Talbot array elimination by means of the Pugh phase distribution, and So, but maybe you might ask, what is pure phase distribution? So, when you are dealing with fields, so this fields actually can have different behavior, sometimes because of the rotation, twisted of the light, twisting of the forces. So and then actually you have different phases. So in Talbot effect also we have different phase distribution at fractional Talbot distances. But what is Talbot distance? Of course, you cannot see this effect in every situation. So we need a special situation. So we need a special distance. So and when you see here, for example, by amplitude grading with opening ratio, so this is about the size of the aperture when you are talking about diffraction. So maybe you ask how we could have diffraction. So you have to just make a small hole in for example in a glass or in a plate, and then if you put this small hole in the front of light, especially when the light is monochromatic. So because of diffraction from the edge of this little hole, then you can see actually the diffraction pattern on the screen if you just detect it. Okay, so far so good, and then we will move on. So this is the picture of Henry Fox Talbot, that he was living in this duration, and so I was explaining what is Talbot effect, but let's just be a little bit more into detail and also talk about a Fresnel diffraction. So I was explaining what does diffraction mean, and but this diffraction actually can be classified in near field or far field. So near field, it means that this diffraction actually can be happen in a close distance from the source, and a far field diffraction, that it's we call it Fraunhofer diffraction. Actually, it can happen in more distances from the source. Okay, now you know what is grading, and now so consider that when a grating is illuminated by a monochromatic plane wave, its self-image is produced by the infinite waves that come from the grating with propagation direction that are determined by the basic grating equation. So this is a beautiful concept, because this grating actually, you see that these gratings also are behaving like the secondary aperture. So you can repeat this diffraction. You can put this grating in a special distance of the source, and then because of so many diffraction, because of the superposition and self-imaging of this diffraction, then you can actually create a Talbot pattern, and you can see the Talbot effect. Okay, so I said about Fresnel near field diffraction. So Augustin Fresnel actually was a French physicist that for the first time he discovered Fresnel diffraction in optics, and actually he was living in this duration, and you can read about his his activities in physics on Wikipedia page. Okay, so now Talbot effect. Let's go to the laboratory. So you need a setup to actually create this effect in your experiment in your laboratory. So if you have a laser beam here, so this laser beam, you can put a lens in front of this laser beam, and then so you can have convergence of these beams in a focal point, and then actually by another lens you can have this light, and then this is a grating here. So this grating, the line spacing is equal A. You put one grating here, and this is a beam splitter, and this is a camera, and also you know what does beam splitter mean. So it means that so this beam simply can be splitted, and so in two different directions. So one goes to the camera, and the other goes to the other direction. And so this is another grating, and you see that here the contrast is 0, and but you have to put the other grating in Talbot distance. And Talbot period, actually, this is A squared divided by lambda, and lambda is the wavelength. Okay, so if you put this the second grating actually in the Talbot distance, and then you can see the maximum contrast in these planes. So and then here you can actually see the self image of the grating, and then you can just put a special object that is just should be uniformly reflective, because this this beam is just is applying to this object, and this object has to reflect, and then because of this emission and refraction and diffraction, so this combination of this optical phenomena, you can see a symmetrical pattern that actually it's optical symmetrical pattern, and it's beautiful and of course applicable effect in optics. Okay, let's move on. But challenge, so at which distance we can obtain the Talbot effect? I mentioned a little bit in the experimental setup, but now let's move on a little bit in mathematics. So the Talbot self-imaging effect is observed at the so-called Talbot distances at C equal NCT. So, okay, what is NCT? So C, Z, or Z, you say. Oh, I say Z. So ZT is the Talbot distance, and N is a positive integer. And you see here, ZT is equal to 2D squared divided by lambda. So lambda is the wavelength of the incident light. So D is the period of the grating, and N is the positive integer. So it means that when it is positive integer, it means that you can repeat this pattern. It's like, for example, you know about Gauss summation. So it's and at the end the Gauss summation. So you know, in series that we had it in mathematics, you can have different series of the numbers. And then so now here also you have patterns. So you're dealing with number of these patterns. And so because of this, so Z actually the Talbot distance can be written in this. It can be defined like a number series, and so ZT equal to d squared divided by lambda. So d is the period of the grading. So grading also, you know that there is a special distance between the bright and dark part of the grading, and there is always a special period in the grading. Okay, so I will show you a grading, and then you can see what I mean. So this is a Talbot array elimination that actually I was using the PowerPoint tools to, you see that Talbot array illumination, so amplitude grading with opening ratio 1 divided by m. So you see that this is a grading, and this is d divided by m, and this is d. So this distances is quite important, and this is incident light. And you can put the second grading here, and then the third grading here, and the fourth grading here. And then so you see that the pure phase distribution at fractional Talbot distances. So in this figure, for the amplitude grading with an opening ratio 1 divided by m illuminated by monochromatic light, the amplitude and phase distribution at all distances of p divided by 2m zt are periodic, where p and m are positive integer. This will be pure phase distribution when p and m have no common divisor. So about divisor, you know that you can actually divide the amplitude of the light, and also you can change the phase of the light. So now I show you that this combination of this grading, but in a special Talbot distance, will create for you a Talbot illumination or Talbot array illumination. Okay. So there are some principles related to Talbot array illumination. So there is the symmetry principle. What does symmetry principle mean? I will show you by some model and also some simulation that I did, and also you see the regularly rearranged neighboring phase difference rule and a complete set of simple phase equation and the prime number decomposing rule and hexagonal Talbot array illumination. And also this effect actually can be used in holograms. But I don't want to talk about the holograms. It's completely another topic that you can actually dedicate a separate seminar to talk about the holograms. Okay, so let's move on and talk about this principle that I listed here for you. So the symmetry principle. So if you check the paper that I was referring at the end of the seminar, so Zhu and his co-workers actually could show that analytically they proved that depending on the fractional Talbot distance involved, there are 4 kinds of symmetries of pure phase distribution. These 4 kinds of symmetries can be reduced to the 2. So we will see it in figure 2. You can see it here. So I will talk about it later. Okay, so depending on whether m is even or odd, the 1 divided by m is the opening ratio of an amplitude grading. The symmetry of the Talbot effect is the basic characteristics of a Talbot array illuminator. So it's about the symmetry principle. So it is better to see it by a model or by a picture. So when we are talking about symmetry in nature, in symmetry, you see pattern. So it means that if you have something on the left side, you have to have exactly the same thing in the other side. This is symmetry. In quantum field theory, always we should have symmetry. And now also you are actually dealing with a lot of fields, with optical fields, and you have to have symmetry. So it's a factor that you can actually check it in your calculation, and so you have to have symmetry. And this symmetric structure of phase factor within one period for even m or odd m. So as I was talking about the distance from different gradings, and which kind of distance we can consider it as a Talbot distance. You know about the formula. So it was d squared divided by lambda, and then actually you can analyze that that if your pattern has symmetry or not. So another actually beautiful pattern that all of us definitely saw it in the nature. So it's a honeycomb that is actually hexagonal Talbot array illumination. So you see that it is just a pattern, and this pattern, you see that the symmetry in this pattern. So it means that if you have, for example, a special structure here, so you have exactly the same structure in the other side. So and you can actually see the symmetry in this pattern. So this is the real example to show, and also I show you at the beginning a carpet that, for example, I would like to one more time go to the carpet. So let's and show. Let's go to the carpet. So yeah. So Persian people always use carpet in the houses, in their homes, and always you see pattern in the carpet. So I told you that maybe I told you that English theoretician, so Michael Berry, so he used the carpet of light for describing the Talbot effect, because you see the pattern actually is made by light. It's like a carpet. Okay, because of this, I chose this picture at the beginning of my presentation. Okay, so let's go to the let's we were here, we were in this symmetry, we were here. Okay, yeah, we were here. So I gave you a real example of hexagonal Talbot illumination in the nature, honeycomb. And this seminar is just a review. It's I just did a simulation that also I derived it from one of the papers. So we just review this effect, Talbot effect, by reviewing the literature that actually was done by theoretician and also experimentalist. So here, and so experimental result. So you see that I chose this picture from this paper that is actually was published in Optics Letter. You can find the name of the authors at the end of the presentation. So they actually could create a Talbot effect in their laboratory, and this is similar to the hexagonal Talbot's illumination, like a honeycomb. So actually in this pattern, so they also measure the distance between the structure, and they actually they use this formalism to actually to talk about this structure in mathematics language. So experimental result of near field hexagonal array illumination at a half Talbot distance of c equal, it's a little bit small, but you can still read it. So z equal z Talbot divided by 2, it's equal 3tx squared divided by 4 pi for lambda. So lambda is the wavelength, and so you see that this pattern actually is half Talbot distance, and I have to also mention about the bright and the dark side of this pattern. So in the bright side, actually, you have constructive interference. So you see that the phase here is pi or p, and the dark side actually. So it's the destructive interference, and you see hole, or you see the the phase is equal to 0. Okay, so that was the experimental result for this pattern. And this is the simulation that I did by using MATLAB. So I also referred to MATLAB software that in my master, also in my PhD, I was using MATLAB software that actually was based on C computer language C. It's mostly used in MATLAB. So you see that I did this simulation. This axis is intensity, this is position. And this is not a difficult code. Actually, you just can use a loop, while do, for example, and then you can actually create this pattern. So this pattern actually should be repeated at a special distance, at the same distance, like this pattern. So you have to have symmetry in your pattern, and you see this symmetry in this pattern. And this is a good simulation to show and see how Talbot pattern can be created by computer or so on. Okay, so so in this seminar I talk about actually Talbot effect. So in conclusion, the Talbot self-imaging effect is a well-known optical phenomenon. In this presentation, some results about Talbot effect and Talbot illumination array have been reviewed. So familiarity with this principles actually can expand our understanding of the Talbot effect and ultimately of Fresnel diffraction. And some references that I used are Zhu et al. And Wikipedia, Rayleigh, and also Talbot. And also I checked the other literature, but it's out of this scope, and it's in more detail. So at the end, thank you for your attention, and see you in the next video. Bye.